Hello, I'm Michael Nelson, and I'm presenting this work on behalf of my colleagues at Old Dominion University, Los Alamos National Laboratory, and New York University. And this project was funded by the Alfred P. Sloan Foundation. And this is about cited but not archived, looking at the status of GitHub links in scholarly articles. So let's start with two facts. Number one, the web is not permanent. And number two, scholars are including links to software and data when they write their publications and publish them in journals, preprint servers, etc. So number one, the web is not permanent. Here we have an example of a GitHub repository that is 404 on the live web. This no longer exists. Now, it's possible it's moved to a different URL, a different name. It's possible that it's been forked, but at the original URL, we can no longer find it on the live web. Now, the problem is that original URL shows up in this case, preprints, and the highlighted section here shows that the full URL of the GitHub URL is linked to in this document. Now, this document is not even quite 10 years old, and the scholarly objects that it links to have been removed from the web. So we can read this paper, but the code, the data, the supporting material is unavailable to us. So what happens when these two facts collide? We have the web, which is not a permanent resource, and the fact that scholarly articles are linking to additional scholarly objects that exist on the web, right? We do a pretty good job of preserving preprints and journals and traditional publication formats, but the things that those traditional publication formats link to, we do not do a good job of saving. And unfortunately, the code and data is not immune to reference rot. So again, we can read this publication from almost 10 years ago, but we cannot access the code or data on the live web. Now, to understand the scope of this problem, we decided to look at two significant corpuses. To begin with, we really wanted to focus on Git and GitHub. Now, it's important to understand that the difference between Git and GitHub, Git is really just a command line interface that allows you to synchronize software and do version control. GitHub is a hosting platform for GitHub repositories. And the best way to really think of this is that GitHub is a superset of Git. So Git exists on the command line and GitHub exists on the web. And really, we want to focus on GitHub as the web representation of things that we do with Git. Now, we often use these interchangeably, but when we talk about GitHub, we're really talking about Git hosting platforms. And there's actually a bunch of platforms, some of which have gone out of favor, like SourceForge and Bitbucket. And GitLab is also a Git hosting platform that's an open source. And GitHub, of course, is owned by Microsoft. So the focus of this study will really be the four main Git hosting platforms. But as we'll see, GitHub is certainly the most popular of those four. But the takeaway is the key word here is hosting platform, not archive. So it's great that GitHub is supported by a large entity like Microsoft, but that doesn't mean that it's an archive and the material is always going to be there. Now, the two main corpuses that we looked at, first was the arXiv.org, originally the physics ePrint server. And this is run out of Cornell. Now, this covers a lot of the STEM disciplines, including those that are, shall we say, computer friendly. So they are more likely to have links to software and data, because if you're going through the trouble of uploading your preprint to a preprint service like arXiv, probably you'll have more links to code and data. There were over 2 million articles we looked at there for arXiv, and they range from 2007 to 2021. And there's an API for us to access. And looking at arXiv, they have versions for their publications. We only looked at the most recent versions, the highest version. The other corpus that we looked at was PubMed Central. And this is the full text journal archive of a variety of biomedical and life science journals. There are over 7 million articles available, and it covered the same time frame for the arXiv corpus. So of those about 9 million publications, 2.66 million of those publications had a link to at least one URI. And the total number of URIs linked to were about 7.8 million unique URIs. And this, and including, counting these 7.8 million URIs, we went through and excluded links to DOIs and URLs that should have been DOIs, like link.springer.com and other deep links to, say, ACM Digital Library, IEEE Digital Library, because authors will frequently provide links to the deep links into the digital libraries instead of linking to the DOI like they should. So we excluded those. The 7.8 million, or at least excluded the popular DOIs. All right, of those 7.8 million links, 235,000, almost 236,000, were links to one of the 4 GitHub hosting platforms. As we can see, of those 236,000, the majority, 216, almost 217,000, are in fact links to GitHub. So GitHub is clearly the predominant GitHub hosting platform. Okay, now that we have this corpus, we can look at 3 main questions. Of these 236,000 GitHub repos, how many still exist on the live web? How many are in the software heritage, a dedicated digital library for GitHub URLs? And how many of these repositories exist in public web archives like the Internet Archive? To query how many exist in the web archives, we used Memgator. Memgator is an open source memento aggregator developed at Old Dominion University by Suud Alam. And basically, it broadcasts your queries to all known public web archives. Of the responses that we got in the public web archives, about 82% of the responses came from either the Internet Archive or known mirrors of the Internet Archive. There were some copies in lesser known web archives like arXiv Today, Archivo, Library of Congress, and so forth. But honestly, if you're doing this en masse, you could probably get away with just querying the Internet Archive. If you really wanted to uncover every last copy, you really do need to check the other web archives, though. Now, to query software heritage, there's actually a problem. So this shows a screenshot of a deep link to one of the URLs extracted from our corpus, and it says no origins matching the search criteria were found. Well, the issue is the Software Heritage API does not support these deep link queries. So for this kind of URL, we had to shorten it, truncate it with known patterns that all GitHub repositories have this form of github.com/the username / the repository name. And in this example, the username is both TensorFlow, TensorFlow is both the username and the repository name. So this was the URL that was linked in the publication, but to query software heritage, we shortened this URL to just the user and repository. For the web archives, we did not shorten the URLs. We queried them as they were linked. So this shows the screenshot of the shortened URI and software heritage saying, oh, yes, in fact, I do have the TensorFlow repository inside. Okay, of the 236,000 GHP URIs that we had, about 94% were still on the live web. And that's actually a really good number. So that gives us about 8,000, almost 9,000 repositories, however, that have disappeared, that are rotten or are unavailable on the live web, and their links no longer work. Of those 236,000 URIs, about 2/3 exist in software heritage. And this is after doing the shortening technique to look and do a query. So about 2/3 exist in the software heritage. About 4/5, just over 81%, exist in web archives. And then if we combine this, we look overall, about almost 55% exist in both software heritage and in web archives. And the takeaway here is there's a small percentage that exists only in software heritage. There's a greater percentage, shown here in orange, that exists in only in web archives. And then the vulnerable, the ones that exist on the live web, but exist neither in software heritage nor in the web archives, that's about 13%, or basically just over 1 in 8 of the URLs exist on the live web, but are vulnerable because we can no longer, they do not exist in web archives or software heritage. So this represents about just over 15,000 of the 115,000 unique GitHub repository URLs that are vulnerable, essentially in need of archiving of some type. So of the 6% of the GHP URIs that have disappeared from the live web, 33% of those, basically 1/3, do not exist in GitHub repository, in software heritage or in the web archives. So essentially, about 1/3 of that 6% are just gone. Short of heroic efforts, we will not be able to recover them. So the takeaway that we have here is, of about 9 million publications, almost 1/3 of those had links to some kind of URIs. And when we look at all those URIs that were linked to and remove all the DOIs and things that are similar to DOIs, we had about 7.8 million URIs. And of those URIs, about 236,000 of those were to GitHub hosting platforms. 94% of those were still alive on the live web, and 67% of those were in software heritage, and 81% were in web archives. 13% were vulnerable, which neither in software heritage nor in the web archives. And of the 6% that were no longer on the live web, 33% of those were not recoverable in software heritage or the web archives. Those are just lost. So if you would like to follow up on this, we have 2 links. There's a GitHub repository, hopefully in both web archives and software heritage, that has the data and the software we use to process it. And then we also have a blog post, since this is based on Emily Escamilla's master's thesis. And I look forward to taking any of your questions. Thank you.